We have just received a startling chemical fingerprint from deep space, and it confirms that our latest interstellar visitor is not behaving like anything we have ever seen before. The data coming in from the NASA SPHEREx mission has fundamentally altered our understanding of the object known as 3I Atlas. We are looking at a significant post-perihelion brightening event that is characterized not by simple dust release, but by a complex, chemically diverse outburst driven by subsurface volatiles. This is the update we have been waiting for. Right now, the object is positioned between 3.8 and 4.0 astronomical units from the Sun, moving away from us at a speed of roughly 40 kilometers per second in the constellation Gemini, while its apparent brightness has dimmed to a magnitude between 13.5 and 14.2, making it a difficult target for amateur telescopes. Professional instruments are capturing a story of unexpected activity. The headline here is the chemical composition of this outburst. We are detecting infrared emissions that reveal a potent cocktail of water vapor, carbon dioxide, methane, methanol, and cyanide. This is not just a rock tumbling through the dark. It is an active, evolving body that is reacting violently to its recent passage through the inner solar system. Before we dive deeper into what these chemicals tell us about the object's origin, if you want to stay ahead of these breaking discoveries in interstellar observation, make sure you seek out that subscribe button so you never miss a briefing. The timing of this surge is critical. We typically expect cometary activity to peak when the object is closest to the Sun, reacting to maximum solar heating. However, this major release of volatiles is happening as 3I Atlas is receding, moving deeper into the cold. This suggests that the heat from its closest approach took time to penetrate the surface layers, finally reaching a reservoir of frozen gases trapped beneath the crust. The presence of water vapor is expected, but the simultaneous and significant detection of carbon dioxide, methanol, and cyanide points to a primitive, chemically rich body. This is the kind of pristine material that has been locked away for billions of years, shielded from cosmic radiation and heat until this very moment. The intensity of these emissions indicates that we are witnessing the shedding of the object's outer skin, or perhaps the fracturing of a weathered crust that is now exposing fresh, volatile, rich ice to the vacuum of space. The detection of cyanide is particularly telling. In solar system comets, cyanide is often a trace component, but here it appears as part of a robust, distinct outflow. This chemical diversity implies that 3I Atlas did not form in a warm, processed environment. Instead, it likely coalesced in the cold, dark outer reaches of a distant star system, far from its parent star's radiation, allowing these volatile compounds to freeze into the very structure of the nucleus. What makes this SPHEREx dataset so powerful is its 102 wavelength infrared capability. This allowed astronomers to not just detect these gases, but to map their relative abundances with unprecedented precision. We are seeing spectral lines that are inextricably linked to the sublimation temperatures of these specific ices. The fact that they are all releasing now at a distance of nearly 4 astronomical units tells us about the thermal inertia of the object. It holds on to heat. It takes a long time to warm up, and consequently, it takes a long time to cool down. We are seeing the thermal lag effect in action, where the peak temperature of the subsurface creates peak activity long after the perihelion point has been passed. This chemical fingerprint also reveals the physical nature of the material being ejected. We are not just seeing gas, we are seeing the ejection of large grains and chunks the size of BB pellets. This is a crucial distinction. A typical fluffy cometary snowball would disintegrate into fine dust. The presence of these larger, substantial grains suggests that the nucleus of 3I Atlas is compact and resilient. It has structural integrity. It is holding itself together despite the violent outgassing that is tearing at its surface. This resilience is contrary to the fragile nature of many comets native to our own system, which often crumble under far less thermal stress. The implications of this post-perihelion brightening are profound. It challenges the standard model where activity is symmetrical around the closest approach to the Sun. Here, the asymmetry is stark. The object was quieter on the way in and is now shouting on the way out. This behavior is a direct clue to the structure of the nucleus, hinting at a stratified interior where different layers are activated at different times. We are seeing the result of a geological sequence of events where the stripping away of an insulating layer has finally allowed the Sun's warmth to tap into a deeper, more volatile reservoir. This chemical surge serves as the foundation for everything else we are observing. It explains the brightening. It explains the dense coma we are seeing in telescope images, and it sets the stage for a specific, puzzling anomaly regarding methane that we need to examine closely. The profile of these emissions is not uniform. The release rates vary, and the ratios of these gases are painting a picture of an object that is chemically distinct from our local comets. We are dealing with a visitor that brought its own unique history with it, frozen in time, and is now thawing out for us to analyze. As we continue to monitor this outflow, the data from SPHEREx is providing us with a baseline to understand the more specific and, frankly, more baffling behaviors of the object. The sheer volume of material being lost right now is significant, yet the object persists. It is not breaking apart. It is evolving. This durability, combined with the exotic chemistry we are detecting, forces us to reconsider how we categorize these interstellar travelers. They are not merely inert debris. They are geologic time capsules, and 3I Atlas has just cracked open its seal. The detection of methanol, in particular, adds another layer of complexity. Methanol is a building block for more complex organic chemistry. Its presence, along with water and carbon dioxide, suggests that the environment where this object formed had the potential for rich prebiotic chemistry. We are analyzing samples from a stellar nursery light years away without ever leaving our backyard. The fact that this release is happening now at such a distance gives us a prolonged window to study these components before the object fades back into the darkness. This active phase, driven by the specific volatiles identified by SPHEREx, serves as the engine for the dynamic changes we are tracking in the object's rotation and brightness. The force of this outgassing is what is propelling the changes in its spin state, acting like a thruster firing continuously into space. But within this broad release of gases, there is one specific element that stands out, not just for its presence, but for its delay. The methane we are seeing now was not there earlier, and its sudden appearance raises difficult questions about the internal architecture of the nucleus. This is not just a mix of gases, it is a structured release that tells us about the layers of history hidden deep inside the core of 3I Atlas. The story of that methane and the paradox of its timing is where the mystery truly deepens. As we established, the chemical surge we are witnessing is broad and intense, but within that diverse cocktail of gases lies a specific anomaly that demands our full attention. We call this the methane paradox. While water vapor and carbon dioxide began venting earlier in the object's journey, the appearance of methane has been significantly delayed, showing up only after the object had already passed its closest approach to the Sun. This timing is critical because methane is extremely volatile. It should have sublimated and escaped long before water did. The fact that it waited until now to emerge tells us something fundamental about the internal structure of 3I Atlas. Specifically, methane now comprises between 14 and 27% of the total water production. This is a substantial fraction, effectively making it a dominant component of the current outgassing. The data shows that the relative abundance of methane is actually increasing as the object departs the solar system. This behavior points directly to a layered nucleus model. It implies that the methane was not present on the surface when the object entered our system. Instead, it was buried deep beneath a crust or an outer layer of other materials. Only after those outer layers sublimated away, stripped by the heat of perihelion, was the inner, methane-rich core exposed to the vacuum. This delayed release suggests that the interior of 3I Atlas has been pristinely preserved. Despite traveling through interstellar space for billions of years, bombarded by cosmic rays and exposed to the harsh environment between stars, the core remained shielded. The outer layers acted as a sacrificial crust, a radiation-hardened shell that protected the delicate volatiles inside. When that shell was finally breached by solar heating, the methane trapped inside was released in a delayed explosive event. This confirms that we are looking at a differentiated body, one that was built up in layers over eons, rather than a homogeneous lump of ice and rock. But the chemical strangeness does not stop with the timing of the methane. We must also look at the ratio of carbon dioxide to water. The observations indicate this ratio is unusually high, sitting between 8 and 10. This is one of the highest values ever recorded for any comet, solar or interstellar. For comparison, most comets in our own solar system have a much lower proportion of carbon dioxide relative to water. This extreme ratio is a smoking gun for the object's formation history. It suggests that 3I Atlas formed in a carbon-rich environment, likely the outer disk of a distant star where carbon monoxide and carbon dioxide were far more abundant than water ice. This high carbon content separates 3I Atlas from the family of objects we are familiar with. It hints at a birthplace that was chemically distinct from the nebula that spawned our sun and planets. We are seeing the signature of a different stellar recipe. The combination of high carbon dioxide and the eventual delayed release of massive amounts of methane paints a picture of a worldlet formed in the frozen twilight of another solar system, specifically in a region known as the carbon monoxide snowline. Understanding this paradox, why the most volatile gas waited the longest to appear, requires us to rethink our models of cometary evolution. In a standard model, volatiles release in order of their sublimation points: nitrogen and carbon monoxide first, then methane, then carbon dioxide, and finally water. Here, the sequence is scrambled because of the physical layering. The geology of the object is overriding the chemistry. The methane could not get out because it was physically trapped. This implies a complex formation process where the object gathered different materials at different stages of its growth, perhaps migrating through different regions of its home protoplanetary disk. The delay also helps explain the continued activity we are seeing at nearly 4 astronomical units. Methane turns to gas at extremely low temperatures. Now that the methane reservoir is exposed, it can continue to drive activity even as the sun's heat fades. The water ice activity will shut down first as the object cools, but the methane and carbon dioxide can keep the vents open, powering jets and expelling dust far longer than a water-dominated comet could sustain. This differential shutdown of activity will likely cause the coma's composition to change drastically over the coming weeks. Building on this, the sheer quantity of methane, up to 27% of the water production, is staggering. It implies that this inner layer isn't just a small pocket. It might represent a significant portion of the total mass of the object. We might be dealing with a body that is, at its heart, a methane world, disguised for most of its journey by a water ice shell. This inversion of expectations is precisely why we study interstellar objects. They challenge our assumptions about how planetary systems are built. If you are finding this deep dive into extraterrestrial chemistry as fascinating as I am, take a moment to leave a comment below. What do you think this high carbon ratio tells us about the star system 3I Atlas came from? I want to hear your theories. This specific chemical delay also connects to the physical behavior of the dust and gas we see. The release of methane is energetic. It expands rapidly. This intense, delayed outgassing provides the thrust necessary to eject the large grains we discussed earlier. It is the engine behind the post-perihelion brightening. The pressure from sublimating methane is likely what is fracturing the remaining crust, creating the vents and jets that define the object's current appearance. This brings us to the visual consequence of this chemical activity. The gas is not just seeping out uniformly, it is bursting out in specific directions, shaped by the geography of the nucleus and the physics of the ejection. This is where the story shifts from chemistry to geometry. Because of a rare alignment of the planets, we have been gifted a view of this process that is nearly impossible to achieve under normal circumstances. We have chemically identified the fuel, but now, thanks to the Hubble Space Telescope, we have images of the engine's exhaust structure itself. The delayed methane is the power source, but the shape of the jets reveals the machine. This connects the chemical violence we have just analyzed to the stunning visual evidence captured by the Hubble Space Telescope. While the chemistry tells us what is happening, the imagery tells us how it is happening. We were incredibly fortunate to catch 3I Atlas during a rare, near-perfect alignment between the Sun and the Earth. The viewing angle was just 0.69 degrees off axis. In astronomical terms, this is effectively looking straight down the barrel of the gun. This specific geometry allowed us to see structures that would have been invisible from any other vantage point. The Hubble data reveals unprecedented jet structures emerging from the nucleus. We are seeing three distinct mini-jets spaced at regular 120-degree intervals. This symmetry is striking and unusual. Typical cometary jets are often chaotic or clumped together on the sunward side. To see three evenly spaced vents implies a high degree of order in the underlying structure of the nucleus, or perhaps a rotational stability that organizes the outflow into this trifold pattern. It suggests that the active regions on the surface are distributed in a way that creates a balanced, almost engineered-looking exhaust plume. Navigating this alignment also revealed an extended anti-tail. This is a sunward-pointing spike of dust that often confuses observers because it seems to defy the solar wind, which pushes dust away from the sun. However, this is widely understood to be an optical illusion caused by our viewing geometry. The anti-tail consists of larger, heavier particles, likely the BB-sized chunks we detected in the infrared spectrum, that have been left behind in the object's orbital plane. Because they are heavy, they lag behind the nucleus, and when we view the orbital plane edge on, as we did during this alignment, these trailing particles appear to project forward toward the sun. This alignment also explains a sudden 20% surge in brightness that was recorded. This was not necessarily an increase in the material coming off the object, but rather an effect of the dust scattering light directly back at us. This is known as the opposition surge or the Seeliger effect. The dust particles, particularly those large grains driven by the methane release, hide their own shadows when illuminated directly from behind the observer. This results in a spike in apparent luminosity. By analyzing this surge, we can deduce properties about the particles themselves. They are not smooth spheres. They are likely rough, porous aggregates that scatter light efficiently in the backscatter direction. The presence of the three mini-jets at such precise intervals also highlights the asymmetric nature of the coma. The gas and dust are not forming a perfect sphere around the nucleus. Instead, we see a lopsided cloud with outgassing patterns that are distinct from typical solar system comets. This asymmetry is likely driven by the non-uniform mass loss we discussed. If the methane outburst is localized to specific fractures or regions where the crust has failed, it creates these concentrated beams of material rather than a global fog. This unique view allowed us to map the morphology of the ejection in 3 dimensions. The jets are not just surface features. They extend far out into the coma, shaping the overall environment of the object. The fact that we can distinguish individual jets at this distance speaks to their intensity and collimation. They are narrow, focused streams of matter, powered by the subsurface pressure of the sublimating volatiles. The anti-tail, while a geometric trick, provides real data on the mass distribution. It confirms that 3I Atlas is shedding significant mass in the form of solid debris, not just gas and fine smoke. These larger particles will drift in the object's wake for millennia, a trail of breadcrumbs marking its path through our system. The visibility of this feature is a direct result of the high volume of dust production triggered by the methane release. If the object were only releasing gas, or only very fine dust, the anti-tail would be much fainter or invisible. Considering the precision of these observations, we must ask ourselves what mechanism maintains such stable jet structures on a body that is shedding mass so violently. The 120-degree spacing might reflect the shape of the underlying nucleus. Perhaps it is triangular or faceted in some way, or it could be a product of the rotation pole's orientation relative to the Sun. A rotating object with active regions at specific longitudes could produce a pinwheel effect that, when viewed from our angle, creates the appearance of stationary jets. The brightness surge, influenced by particle composition, also gives us clues about the porosity of the dust. These grains are likely fluffy, fractal-like structures rather than solid pebbles. This fits with the idea of a pristine, ancient body that has not been compacted by gravity or heat. We are seeing the raw building blocks of planetary formation, gently stuck together and now blown apart by the pressure of escaping gas. Given what we now understand about the ordered chaos of these jets and the optical physics playing out in the tail, we have to look at the motion of the body itself. These jets act like rocket engines. If they are not perfectly aligned with the center of mass, and the asymmetry suggests they are not, they will impart torque to the nucleus. They will make it spin, and not just spin, but tumble. The stable symmetry of the jets captured by Hubble is only one frame of a much more dynamic movie. To see that motion in action, we need to turn to the continuous monitoring provided by the TESS mission, which watched this object not for minutes, but for days. This brings us to the dynamic behavior of the nucleus itself. While Hubble gave us a snapshot of the structure, NASA's TESS mission provided the movie. In a dedicated campaign, TESS compiled a 28-hour continuous video sequence constructed from 36 individual frames. This high-cadence monitoring revealed that 3I Atlas is not rotating smoothly. It exhibits unstable rotation with varying periods, a state often referred to as tumbling or non-principal axis rotation. The light curve, the graph of the object's brightness over time, shows periodic fluctuations that do not repeat perfectly. A simple, spinning top would give us a clean, predictable sine wave of brightness. 3I Atlas gives us a messy, complex signal. This indicates that the nucleus is tumbling end over end, likely spinning on multiple axes simultaneously. This chaotic motion is a direct result of the outgassing we have been discussing. The jets of methane and water are acting like thrusters, but because they are distributed asymmetrically, they are applying torque in random directions, constantly destabilizing the spin. Along with this tumbling motion, TESS observed an overall fading inactivity during the observation window. The peaks in brightness were getting lower, and the troughs were getting deeper. This fading is a signature of the object moving away from the Sun and the activity beginning to wind down, but it also hints at the exhaustion of specific active vents. As a pocket of volatile ice is depleted, the jet shuts off, the torque changes, and the spin evolves. We are watching the object reshape its own motion in real time. Ground-based observations from major telescopes like Gemini North, Subaru, the VLT, and Keck have corroborated this picture of instability. They depict an increasingly asymmetric coma dominated by dust. The main tail, which is usually the most prominent feature of a comet, has nearly vanished in these recent images. What remains is the weak anti-tail we analyzed earlier, and a diffuse, lopsided cloud of dust surrounding the central point. This lack of a strong main tail further confirms that the fine dust, which usually forms the tail, has been blown away or has ceased production, leaving only the larger, heavier grains that linger near the nucleus. The link between the coma's shape and the nucleus's spin is crucial. As the object tumbles, different faces are exposed to the sun. If one side has a large active region and the other does not, the amount of material released changes drastically as that face rotates into and out of the sunlight. The reprocessed spectra from the Mars Express and ExoMars Trace Gas Orbiter flybys have been instrumental here. They link the observed brightness asymmetry directly to this coma rotation. We can effectively see the weather on the comet changing as it rotates. This chaotic spin also complicates our attempts to measure the precise size of the nucleus. If we don't know the exact orientation, it is hard to interpret the brightness data. However, the fluctuations give us constraints. The fact that the spin is changing implies that the mass of the object is low enough to be pushed around by gas pressure. A massive planet would not notice a geyser on its surface, but for a small cometary body, a strong jet is a significant mechanical force. The fading activity observed by TESS offers a clue to the nucleus's venting mechanism. It suggests that the vents are not continuous pipes, but perhaps cracks that open and close as the thermal stress changes. The unstable nature of the rotation might even be stressful enough to cause landslides or structural failures on the surface, which would trigger fresh outbursts of dust and gas. The video data essentially shows a body that is physically convulsing as it recedes into the dark. Interestingly, the periodic brightness fluctuations are not just random noise. There is a pattern within the chaos that allows astronomers to tease out the spin rates. While the period varies, it generally falls within a range that suggests a relatively fast rotation, which helps explain the centrifugal force needed to eject the larger particles. If it were spinning too slowly, the heavy dust might simply fall back onto the surface. The spin helps fling it out into the coma. The TESS data complements the chemical data from SPHEREx. SPHEREx tells us what is leaking out. TESS tells us how that leakage is physically moving the body. The delay in methane release we discussed earlier aligns with this. A sudden, late burst of gas from a new location would provide exactly the kind of kick needed to induce the tumbling motion we are seeing now. We are witnessing the mechanical consequences of the chemical paradox. All of these factors, the tumbling, the fading, the asymmetry, point to a nucleus that is small but incredibly influential on its immediate environment. The interactions between the solid body and the cloud of gas it has created are complex, and feedback loops are everywhere. The spin affects the mass loss, and the mass loss affects the spin. This dynamic, unstable behavior is typical of comets in their death throes or diverse active phases. But for an interstellar object, it provides a unique opportunity to estimate its physical properties. By modeling how much force is needed to cause this specific wobble, we can start to weigh the object. We can move from observing its light to calculating its substance. And when we run those numbers, combining the motion data with the brightness constraints, We find that 3I Atlas is not just another rock. It is a giant among visitors. Given what we now understand about the forces pushing this object around, we can finally refine our estimates of the object itself. The latest analysis has pinned down the nucleus diameter to 2.6 kilometers, plus or minus 0.5 kilometers. This assumes an albedo, or surface reflectivity, of roughly 4 to 6%, which is as dark as fresh asphalt. This size is significant. It makes 3I Atlas the largest and most massive interstellar object we have ever observed. The mass estimate is equally impressive, coming in at 5 to 7 times 10 to the power of 12 kilograms. To put that in perspective, this object is over 40 times heavier than Borisov, the only other confirmed interstellar comet we have studied in detail. It is a true heavyweight. This substantial mass helps explain why the nucleus has remained resilient despite the violent outbursts and the mechanical stress of its chaotic tumbling. A smaller body might have fragmented under the pressure of the methane release or the centrifugal forces of its spin. 3I Atlas has the gravitational self-gravity to hold itself together. Polarimetry data from the Gemini and VLT telescopes adds another dimension to our understanding of this physical structure. The observations reveal a deep negative polarization branch of minus 2.7% at a phase angle of around 7 degrees, with an inversion point at roughly 17 degrees. In plain English, this measures how the dust grains scatter polarized light. These specific numbers indicate unique dust properties. We are likely looking at large, fluffy aggregates or an unusual mineralogy that is not common in solar system bodies. This reinforces the idea that the materials building this comet compacted in a completely different stellar environment, perhaps one with different dust grain sizes or magnetic conditions. The European Space Agency's JUICE mission has also weighed in, confirming ultraviolet signatures and the presence of dual tails. The plasma particle data collected by JUICE adds to the picture of a body interacting with the solar wind, creating a complex bow shock as it travels. These findings position 3I Atlas as the most active interstellar visitor yet. It is not just the biggest, it is the most dynamic. The exotic chemistry, the stratified structure implied by the methane delay, the symmetric jets, and the sheer durability of the nucleus all paint a picture of an object that challenges our standard models. Anomalies like the early activation at 3.5 astronomical units, the minimal non-gravitational acceleration despite the jets, and the distinct lack of a main tail in later stages suggest that we may need to revise our theories of how interstellar objects evolve. This is not a standard comet. It is a durable, layered, carbon-rich traveler that has survived a journey of light years. As it approaches Jupiter, passing at a distance of 0.36 astronomical units, the gravitational influence of the gas giant will be the final chapter in its solar system adventure. However, by that point, the activity is expected to fully subside. The methane will deplete, the crust will refreeze, and the object will go dormant once again. The focus of the scientific community will then shift from real-time observation to archival analysis. We have terabytes of data to sift through, and the secrets of 3I Atlas likely lie hidden in the numbers we have already collected, but have not yet fully understood. This brief, violent visit has given us a glimpse into the chemistry of another star system. It has shown us that the galaxy is populated by bodies that are both familiar and deeply alien. We have learned that delaying methane release can preserve ancient ices, that tumbling rotation is a natural consequence of stratified outgassing, and that interstellar objects can be massive, resilient survivors. The story of 3I Atlas is far from over. As it fades into the dark, it leaves us with more questions than answers, which is exactly the way science advances. We will be studying this data for decades. If you enjoyed this deep dive into the latest science of the unknown, please hit that like button to help boost this content to other space enthusiasts. It really helps the channel. Only by analyzing these fleeting visitors can we hope to understand the universe beyond our own sun. Thank you for watching.